In my latest experiment video, whereby I blew up a capacitor, I mentioned that I needed a higher voltage tuning capacitor for L2. When I measured the value of the old capacitor tuning board, I noticed it was only half the capacitance of what I thought it was. I will now clarify this and will also show you how I discharge these high voltage capacitors with a resistor, because when you do this wrong, the diodes can be broken. Hi, my name is Ivo and I'm doing research into Nikola Tesla's radiant energy, which is based on impulse electricity. I'll first show you how to discharge the high voltage capacitors with a resistor, and after that I will talk about the new tuning capacitor for L2. Discharge resistor size. After working with the circuit, the high voltage DC capacitors are charged up to a dangerous level. When the circuit is turned off, they slowly start to discharge by themselves, but they are still very dangerous. In the video I showed my power resistor, but I need to explain how I discharge them because I use more than that alone. I use a 896 ohm power resistor that I made by putting 4 220 ohm 17 watt power resistors in series. This big resistance limits the current of the discharge. That is very important because the MER 8100 EG diodes will feel this discharge current and they might blow up if the caps are discharged too quickly. I measured the voltage with my oscilloscope using my high voltage probe. The voltage is probed in DC mode. Okay, let me first explain the circuit. I have a switch and I have a coil that is being switched and is grounded. I supply positive voltage to the coil by means of the switch. When I close the switch, the coil charges up a magnetic field. When I open the switch, that magnetic field can't go anywhere, so the coil starts resonating. Then the signal will look like that. It starts ringing and it will die off due to the resistance of the coil. Now I only want to have this part, which is the negative impulse. So instead of using a physical switch, I'm using a MOSFET switch. And a MOSFET has an internal body diode. And this is really important because each time that sine wave becomes positive, so this section, then it will pass through the diode back into the power supply. And then I will be left with only this part, only the negative impulse. So that is brilliant. Thank you, inventor of the MOSFET. So to deal with that body diode, I need to change the circuit a little bit, and then we have the MOSFET with the body diode internally always present in the MOSFET. Then I'll have a capacitor to capture that positive waveform and a diode to block that positive waveform. And then the positive voltage supply comes in on top of the diode. So that is the basics. So at this point here, I'm gonna probe my oscilloscope with a high voltage probe. Then you can see impulses will be created on the negative, and the positive won't be created because those will all be flowing back through the body diode into that capacitor over here. And then the next cycle, when I switch the MOSFET again, it will be reused. So that makes it very efficient. That's really nice. And we end up with only one polarity impulses. That's what we need. So what I will use is part of the circuit that I always use, the radiant power circuit. And that is like this. I have a capacitor in parallel with the coil. And this capacitor will then have a diode towards ground. This makes it impossible for the positive power supply to flow through the capacitor and charge it up with positive voltage, because that diode is blocking that positive voltage. When the capacitor is turned off, we get that negative impulse, and that negative impulse, what is existing here, will then charge up the capacitor, because we have a diode that conducts that negative voltage impulse towards the ground. This will become positive due to the shifting of the voltages, but I won't go into that. Of course, what I'm using is two MOSFETs in series to produce very high voltage impulses, and that means that the diode at the ground also needs to be doubled, because they can only handle 1000 volts. So I will use 3 diodes in series, and this way I can handle 3 kV. Once this is done, I will have a DC voltage over here, positive. I can discharge that voltage by simply putting a resistor over the capacitor. Then the energy burns away, and that's all good. But with the whole radiant circuit, that's not as easy as normally as you would suspect, because then we would have 2 more capacitors and we can discharge them all at the same time, but then the diodes are in the circuit and are able to break down, because they can only handle 16 amps peak current. They are all 8 amps continuous, but they can handle a 60 amp peak, and a capacitor discharge like this will be a peak discharge. So that's the basics of the schematic. Okay, let's look at this setup. Here's the MOSFET switch. I've got 2 MOSFETs in series. I've got the capacitor parallel over the MOSFET. I got my diodes over here to block the positive voltage that comes through the body diode, passing back into power supply, just so the positive voltage of the coil will return into these capacitors to be reused in the next cycle. And my coil is connected up from the source of the MOSFET to ground, which is over here, and I have the capacitor over here with the diodes, and this is also connected from source to capacitor, from capacitor to diode, from diode to ground, as I just drawn and showed you. There is another capacitor bank over here that I usually use for the L2 coil, but this won't be used right now. I have shortcutted the capacitor over itself, so this won't be able to hold any charge, as it is a shortcut. So in fact it's only this. I got 4 capacitors, 4 times 0.68 microfarad in series parallel, so they can handle 2 times 2000 volts DC, and the capacitance is now again 0.68 microfarads, so 680 nanofarads. I've got my high voltage probe connected to the source also, so I can see the impulses, and this is very handy because I will need to keep an eye on the voltages. I'll need another probe because I want to show you the voltages that I measure on this capacitor bank. So let me hook that up for you. So I connected up another high voltage probe between the capacitor and the diodes. Between that capacitor and between the diodes, I put up the probe because that's where the DC voltage is. I will now turn on the oscilloscope and show you the results of this setup. You can see the oscilloscope here. Yellow is the impulse probe at the source of the MOSFET, and orange is the capacitor probe that will show the DC voltage. So I've got channel 3 here, which is the orange one, and it is put to DC. Let me turn up the voltage again, slowly starting from 0, because we don't want to charge those diodes. I'll put a signal on and I'll dial in some voltage. Now the L3 starts rising again. I've got another injection of DC voltage. Right now it's 2000 volts DC, as we have 4 divisions of 500 volts, and we can go higher to 3000 volts DC, but I think I'm gonna keep it like this. This is a good setting. We've got between 2 and 2.5 kilovolts inside the capacitor bank right now, and the impulses are around 1000, 2000, yeah, 2400. The power supply is now at 23.5 times 2 volts at 0.11 amps. Very efficient at 36 kilocycles per second. I'll turn the system off right now, and there the voltage drops. The orange line of L3 slowly starts dropping again. So it discharges by itself, but it doesn't do it all the way, and sometimes you want to discharge it immediately. So here is my discharge resistor again, 4 times 17 watt power resistors of 220 ohms, making together 896 ohms of resistance, which makes it safe for the high voltage to be discharged. I connected 2 leads up to them, and one lead is with a wooden rod, so I don't have to come near the high voltage part of the circuit. So I can safely put one side of the resistor on the source side, and that is safe because that is basically grounded through the coil. The other side, I don't want to come near that because that's dangerous. If I touch it, I will have a big problem. I don't want that. I'm not even grounded, which I usually am with working with my circuit. But when I'm discharging the capacitors, I do not want to be grounded, as it is dangerous. And with this, I can simply guide that to the high voltage side of the capacitor and discharge it, and even discharge other parts which aren't charged at all, but still it's always good to check and discharge. So I will show you now how that looks like. I'll first charge up the system, then I'll turn it off and immediately discharge it through the capacitor. So a small calculation with the Ohm's law gives 2500 volts divided by 896 ohms will give me 2.79 amps maximum. Now let's take a look at how that looks. I'll go up to 2.5 kilovolts right there. Okay, now I'll turn the system off and immediately discharge. So everything's fine. Recording, yes. So turn off. I have voltage, and you see there's a small spark and almost no bang because the current is limited by this resistor, and it's already fully discharged to 0 volts. So this is more than enough. With this high voltage, I only work with my right hand. My left hand stays in my pocket. And that is a safety guide that saves you a lot of distress, because when you discharge through 2 hands, the charge goes through your body and can go through your heart and stop your heart. And that is very lethal. So that's why I use this. I won't touch the high voltage side, and I only use my right hand. To conclude, when you use a resistor to discharge the capacitors in the circuit, and you have a large spark and a flash and a bang, then you'll risk blowing up your diodes due to the high discharge currents, which also move through the diodes. So you need to use a larger resistance, which limits the current. It then will take more time to discharge, but it will protect the diodes. You can use Ohm's law to calculate a resistor size that limits the current to 16 amps, which is the limit of the diodes. Now I will show you the new tuning capacitor. In my previous experiment I blew up a 1 nanofarad capacitor, which is part of my tuning board. I replaced this capacitor and I measured the capacitance of the tuning board so I could reproduce it exactly for the 4000 volt tuning board. But to my surprise, it was only half the capacity of what I expected it to be. In the video I said that the L2 and L3 coils capacity were equal in size, 121 nanofarads. But it turns out that the L2 tuning capacitor board was only 61 nanofarads in the experiment. This was due to a hookup mistake by me, because I added 60 nanofarad in parallel with the board to make it bigger. But I hooked it up wrong and it wasn't in circuit at all, so I only had 61 nanofarad. This is my old tuning capacitor board. I say old, but I still use it. But this is the one that I repaired. One of the 1 nanofarad capacitors was blown up. I replaced it and I measured it. And then I came to the conclusion that this section which I added wasn't in the circuit at all. I connected it wrong. And so I thought I was experimenting with 121 nanofarads. But actually I was experimenting with 61 nanofarads, as if this wasn't even there. So I made a new tuning capacitor bank, which is this one, based on 121 nanofarads. And it's not finished yet. These are 22 nanofarad capacitors, all 2000 volts DC capable. And what I've done is made 2 rows in series. So I've got 12 in parallel and those are in series, which doubles the voltage capacity. And the total capacitance is right now 131 nanofarad, but they can handle 4000 volts, and that is what I need to be able to do my experiments. So yeah, now I found out that I didn't use 121 nanofarad, so this is way too big and I need to decide if I will experiment with this. I think I'll do some tests and just make it the way it should be. Some of you have asked me to show this tuning process, to show you how it works, but it is very hard to explain for me as it is a very intuitive process. I just play with the frequency and the size of the capacity of L2 and L3 until I see what I need to see. Almost always I aim for the maximum simultaneous amplitude of L2 and L3. So when tuning, I will dial in the maximum sine wave of L2 and then I'll tune in the maximum sine wave of L3. Now they should be at the same frequency, but they won't always be at the same frequency. So I change the capacity of L2 or L3 to match it to the same frequency. When both L2 and L3 are maximum at the same frequency, then both are resonant at the same time. And this is what always is my goal with tuning. This is all part of my open source research, which means anyone can benefit from this freely. Use it as you see fit. No patents can be applied. If you want to fund my research, you can do so by leaving a donation on my PayPal account, which is listed below. One more thing. Until now, I used Magic's Video Pro X as my video editor. And to be honest, it gave me a lot of frustrations. I was not happy with it. So I have now switched to DaVinci Resolve, and it is such a relief to finally be able to edit my videos with much quicker, and I'm just very happy with it. Remember to subscribe, leave a like and hit that notification bell for updates on my new videos. And if you have any questions, you can leave a comment in the section below this video. That's it for now. Thank you for watching and see you next time.